In the next several videos, we're going to talk about the atmospheric global circulation, or the wind patterns that go all around the globe. These patterns can be quite complex, and so we're going to break it down and simplify things. And we're going to start with the one-cell model. The one-cell model is also known as the Hadley cell model, and the name comes from meteorologist George Hadley, who was a pioneer in wind understanding, and he really came up with the foundation for this one-cell model all the way back in 1735. The one-cell model is going to make two very large assumptions. The first assumption is that we're going to assume the Earth is not rotating. And the second assumption, we're going to assume that the Earth is covered with a large body of water. In the first assumption, by assuming the Earth is not rotating, we can eliminate the Coriolis force, which is good because the Coriolis force can be quite complicated, as you probably have found. The second assumption actually isn't that big of a deal because 70% of the Earth is in fact covered by water. Why do we make these assumptions? Well, because it's going to make things more simple. And even though it's not going to be perfectly correct, there's still going to be some truth in there. What's going to happen with the one-cell model is you're going to have a single thermally driven convection cell in each hemisphere. Let's take a look at how we get there. We're actually going to draw out the one-cell model using the causal continuum that we talked about earlier. So I'm going to draw three surfaces, the North Pole, the equator, and the South Pole, and I'm going to label the area at the surface and the area aloft. Then we can go down the list of the causal continuum, starting with radiation. Are we going to have radiation differences? Based on what we discussed in the Earth-Sun relationship unit, we know that the equator is going to get more radiation than the poles. Next, we're going to have some temperature differences. Because the equator is getting more radiation, it's going to be warmer than either the North Pole or the South Pole. So I've shown you that with the colors red versus blue. Red meaning warm, blue meaning cool. If you have temperature differences, you'll then get density differences. In order to show you this, I've drawn out the molecules of atmosphere above each of these locations. Above all three locations, you'll notice that the molecules are more bunched up at the surface compared to the upper atmosphere. We know this to be true because gravity wants to pull everything down towards the surface. But if you look at that equatorial column compared to the polar columns, you'll notice that in general the molecules are more spread out, and that's this characteristic of less dense, less compact. If you have density differences, you'll then have pressure differences. Remember, we think of pressure as the weight of the atmosphere. If you count up how many molecules I've drawn above each of these three locations, you should get to 7. And so it appears that there are no differences in pressure. But what if we look at this area aloft? If you look at the area aloft, you'll notice you still have one molecule left above you at the equator, whereas at the South Pole and North Pole, there's no molecules left because everything's more compact there. Based on this, we do in fact have a pressure difference aloft. We have high pressure above the equator and low pressures above either pole. With pressure differences come wind. And so wind is going to blow from high pressure to low pressure. Because of our first assumption that the Earth is not rotating, we don't have to worry about deflecting these winds because we don't have any Coriolis. And so this is our upper level wind pattern. Since wind is the movement of air molecules, we're essentially going to steal weight from the equator and add it to the poles. And so we're going to actually change our surface pressures. Since we're taking weight away from the equator, it's going to be a low surface pressure. Since we're adding this weight to the North Pole and South Pole column of atmosphere, it's going to lead to high pressures. And once again, if you have pressure differences, you'll have wind blowing from high to low. To complete these convection cells, we can also show that we're going to have rising motion where the winds are colliding at the surface low at the equator, and we're going to have sinking motion as that air leaves the surface at the poles, and something has to fill that void, so it comes from above. And so notice we have our two separate convection cells, one in each hemisphere, as we said we were going to have. And so to summarize all of this, we can break it down into what's happening aloft versus what's happening at the surface. In the upper atmosphere aloft, we're going to have an equatorial high and a polar low. Winds are going to flow from the equator to the poles. At the surface, we're going to have an equatorial low, and we're going to have polar highs, and winds are going to blow from the poles to the equator. This is our one-cell Hadley cell model. While the actual circulation of the Earth doesn't look exactly like this, there is some truth embedded within, which is why we use this model. We'll talk about where these truths are in the next video.